In this section, we talk about improper integrals. Basically, this will be a definite integral that represents the area of an unbounded shape. So either our bounds are going to go to infinity or negative infinity, like we see in figures 1, either going to positive infinity or negative infinity, or perhaps both. Or our bounded region contains a vertical asymptote. So for example, we can see this integral. It looks like it's fine until we realize, wait a second, from negative 2 to 2 contains the x value of 0, and 0 causes this function to be undefined. So that's going to cause this to be an improper integral, the result being an unbounded region. It goes on forever. Same thing with this one. 0 to 2 looks fine until we remember, oh, wait, 0 is not a value that's allowed in this function. So how do we deal with these analytically? Well, we have to use limits. We can't plug in infinity. We can't plug in values that cause undefined values in our output. So we have to ask the question, what happens when our definite integral approaches the improper integral? So we replace, if the upper bound is the problem, we'll use b. If the lower bound is the problem, we'll use a. This is just a convention. We don't have to do that. But we replace the infinities with b's, or negative infinities with a's, and we let those a's and b's approach negative infinity and positive infinity. Likewise, over here, since 0 was the problem, we're going to let b approach 0 from the left, or a approach 0 from the right, depending on which side we're evaluating. Okay, so make sure when you're dealing with finite values, we're going to use a one-sided limit, right? So if we're coming towards the bad value of 0, the undefined value of 0, from the right, we're going to put 0 plus there, just like we did down here. So once we get that notation down, then everything kind of falls into place with these guys. So let's take a look at some examples. These 3 examples are all fairly related. Notice that they're all 1 over x raised to a power, where in this case p equals 1, in this case p equals 2, and in this case p equals 1/2. Okay, so we're going to ask the question, what happens with these guys? So before we jump into the analytics, let's look at the pictures. Okay, so I'm going to pull up a graph of Desmos here, and the red right here talks about when p equals 1. When we have 1 over x, we're finding the area bounded by the region from x equals 1 to infinity. Okay? The next one we have is when p equals 2. We've got 1 over x squared. Looks pretty much the same, right? Same basic shape. And then if we look at the last one is 1 over the square root of x. And again, basically the same idea. So we're starting at the same point of 1, 1, and from there, we have a horizontal asymptote of 0, and we just approach 0. So all of these are unbounded regions, and we're going to try to find the area of each one of these. So let's start with when p equals 1. We've got 1 over x. So the first thing is we rewrite this so that the infinity gets replaced with a variable, and we let that variable approach infinity. Then each time, I want to make this color-coded, so we're using red for 1 over x. We're going to take the limit. I thought this was on red. We're going to take the limit as b approaches infinity of, well, the antiderivative of the natural log of x, of 1 over x is the natural log of x, and we'll evaluate that at the bounds of b and 1. So that tells us we're going to take natural log of b minus natural log of 1, and we're going to let that expression, we're going to see what that expression does as b goes to infinity. And we've talked about this before. The natural log function grows slowly, but it grows without bound. There's no horizontal asymptote on the natural log graph. So this guy right here goes to infinity, and this one doesn't really matter what it does. I guess if it went to infinity as well, we'd have a problem, but it goes to 0. It is 0, in fact. So an infinite value minus 0 is still infinity. Oh, so the bounded area, which is infinitely large, has an infinite area. What a surprise. Actually, that's not surprising at all. We say, when this happens, we say the integral diverges. Integral diverges. And you might be saying, well, isn't that always going to happen? If we have an unbounded region, if our region is infinitely large, isn't the area going to be infinite? Well, if that were the case, we probably wouldn't devote an entire section on it. In fact, we'd devote an entire chapter on it after this section. So chapter 9 has to do a lot with diverging things. So yeah, it's not always going to diverge. Sometimes it will converge to a finite value. So let's take a look. If we try this same thing, and I want to make sure I use the same colors. It looks like I used purple. So let's get purple out here. And we rewrite this. We let the limit as b approaches infinity of 1 to b of 1 over x squared, which I'll write as x to the negative 2. All right, so that lets us do the inverse power rule, right? So we've got the limit as b approaches infinity of negative 1 over x, negative x to the negative 1. Evaluate that at b and at 1. So I'm going to go ahead and factor out the negative just because it makes things a little cleaner. And we've got 1 over b minus 1 over 1. And we know that if we take 1 divided by an infinite value, this thing is going to go to 0. And this is just 1, so we've got negative 1, which is positive 1. All right, so this integral does not diverge. This integral converges to 1. And I want to pause for a moment and make sure we fully appreciate this difference between these two problems, because they look pretty similar on the graph, right? We're not talking about this one yet, so let's hold off on that. But if we look at those two graphs, the red one being 1 over x and the purple one being 1 over x squared, they both look kind of the same, but the area of the red is infinite, and the area of the purple is not only finite, it's just 1. Even though both of these regions go on forever, the difference between their sizes is vast. Okay? And it's not surprising that the purple is smaller than the red. We can look at it and we can see that the purple graph is always below the red graph. So it's not surprising that it's a smaller value, but it may be very surprising to some of you. To me, I'm one of those people where it's like, my goodness, that's crazy. The red is infinite. It doesn't look that big, but it's infinite. Okay, well, if the red is infinite, then what's the purple? The purple's just 1. That's just craziness. Anyway, it all bears out. As x gets bigger and bigger and bigger, we're accumulating more area. But in the purple, we're not accumulating enough more area for it to grow without bound. It levels off at 1. Whereas the red, again, does not have a bound. It keeps on growing and growing and growing without bound forever. All right, fantastic. And then we've got one more to do. Let's see, what color is that? That one is blue. So let's go to blue here. And we'll do the same thing with this one. We're going to take a look at the limit as b approaches infinity of the integral from 1 to b of x raised to the negative 1/2 dx. All right, so we'll rewrite that limit again. And this time we'll bump this exponent up by 1 to get 1/2. And the reciprocal of 1/2 is 2. We'll evaluate this expression at b and at 1. I can factor out the 2 to make it a little cleaner. And we're going to look at the square root of b minus the square root of 1. Okay, well, the square root function grows without bound. It grows probably faster than the natural log function, in fact. So this thing goes to infinity as b goes to infinity. And this is just plain old 1. So infinity minus 1 is still infinity. 2 times infinity is still just infinity. So we can conclude that this integral, this third integral where p equals 1/2, will also diverge. All right, now that perhaps is not super surprising, because looking at the graph, we'll see that that blue, the 1 over the square root of x, is bigger than the red. And if the red was already, let's go ahead and get that shaded in there. If the red, which is the first one we did, was infinite, and the blue is bigger than the red, well, if it's bigger than infinity, it's still infinity, right? So that's not particularly surprising, but it is interesting to see the relationship between these three different graphs. And And again, this is planting the seeds for sequences and series in chapter 9. So these three problems right here, these three examples are extremely important. So please make sure you understand them.